Coming at you from Corona quarantine in my Corona bunker. I wanted to make a video going through the first aircraft fire detection systems PowerPoint. That's what we're going to be looking at this morning. Hope you all are doing safe. Let's get started. First thing, fire detection systems will be going through 5/21. May 21st, we have 1.5 hours of fire detection systems until we move on to aircraft coverings, fabric coverings. First off, the classes of fire, we'll run through those pretty quick. Hopefully you know those by now. Class A, ordinary solid combustibles, wood, cloth, paper, upholstery, that kind of thing, you know it. B, flammable petroleum-based fluids, oil, gasoline, that kind of thing. C, fires involving energized electrical equipment. Our best agents, carbon dioxide and halogenated hydrocarbons. And Class D fires, flammable metals. Magnesium is the frequently used example here. The best agent is dry powder, and we know never, ever, ever use water on a Class D fire. Water is going to make a magnesium fire much, much worse. So in fire detection systems, we need as many of the following features as possible. The system must be constructed and installed in a manner that prevents false warnings. Hopefully that makes sense to you, why we can't be having a lot of false warnings. Think about the boy who cried wolf. If I start getting a lot of false fire warnings, what's going to happen when I get a real one? I'm probably going to disregard it. We also need the system to give a rapid indication of a fire and an accurate indication of the location of the fire. If it just tells us there's a fire, but we don't have any idea where it is, that's not going to help us that much as well. We also need an indication when the fire goes out. If I discharge a fire bottle, I need that detection system to let me know that the fire has gone out or that it hasn't gone out, and hopefully I've got another shot of extinguisher to put to it. And we need it to automatically reset once the fire is out and provide immediate indication if the fire relights. So if the fire goes out, we need it to tell us that. If the fire comes back, we need to know that as well. We can't have like a one-use type system here. We need the detector to indicate continuously for the duration of the fire again. Otherwise, we're going to get confused. Is the fire out? Is it not? How do we know? And there must be a means of electrically testing the integrity of the detector circuitry from the cockpit. So we need a way to test the fire detection circuitry so that if we have a bad bulb, a bad wire, that type of thing, we know that before we get a fire and now our system doesn't work. So you're going to see push to test lights on our fire detection systems just to verify that the circuitry is working correctly. The detectors must resist exposure to oil, water, vibration, extreme temperatures, and maintenance handling. They need to be pretty tough. If they're not tough, chances are they're going to malfunction in some of the environments where they're going to have to operate. We like them to be lightweight and easily adapt to any mountain position. And they must be able to operate from aircraft's power system without inverters. Do you remember what an inverter is? DC to AC, AC to DC? Leave a comment. Let me know that you're still up to date on that stuff. Other requirements, minimal electrical current requirements when not indicating a fire. We shouldn't have a large power draw on these detectors when they're not alerting us to a fire. And they should activate some type of warning, such as a cockpit light and or an audible alarm. Most have both. You're going to get a light and you're going to get an audible alarm. We need a separate detection circuit for each engine. Again, if we have 3-4 engines and the fire detector just tells us we have an engine fire, where is it? How are we going to make the decision where to apply our extinguisher? The purpose of a fire detector system: to activate a warning device in the event of a fire. That makes sense. We get a fire, our detection system detects it, sends us a warning. Now it's up to us on what steps to take to extinguish it. Here we are looking on slide 18 at the classifications of the different fire detection systems. Up there in black, you can see the first observation by crew members. Well, this is the classic method, but in larger aircraft, this is not going to work. We have overheat detectors. Overheat detectors detect an overheat condition. The rate of temperature rise makes no difference. Once we are past a certain temperature, this overheat detector is going to send out an alarm. Rate of temperature rise detectors, these are different. These detect the rate of temperature rise rather than just a temperature above a given point. These can be used in areas that are going to get warm. Think of engine nacelles and that kind of thing. But typically they're going to warm up relatively slowly compared to if you applied a flame to them. And we also have infrared flame detectors. They're going to detect the infrared light given off by a flame. So the different overheat detectors we're going to talk about: thermal switches, Fenwall spot detectors, Fenwall continuous loop systems, Kitty continuous loop systems, Lindbergh continuous element. Make sure you keep continuous loop and continuous element straight. They are two different types of systems. And the Systron Donner continuous element system. First up, the thermal switches. A thermal switch is a bimetallic thermostatic switch which is heat sensitive and completes a circuit when heated to a specific temperature. Here you can see in the photo, we have our shell. This is the metal case that the thermal switch is encased in. And we also have two contacts. You can see our shell is grounded and our contacts are held by two thin strips of metal. Looking at this, you can see as the case of the thermal switch starts to expand, it's going to draw those metal bands together and we're going to close those contacts. Again, this is an overheat detector. Not concerned with the rate of temperature rise. Once it hits a certain temperature, those contacts are going to close. Obviously, this is going to be determined by the construction of the thermal switch. Thermal switches complete a warning circuit to ground when they hit their specified temperature. That's where we're going to get our alert. Normally, the thermal switches are going to be wired in parallel to each other and in series with the warning light. Hopefully that makes sense. If I was to connect a bunch of thermal switches in series and one thermal switch had its contacts closed and went to send a signal, is that signal going to get to the cockpit? No. Thermal switches have to be wired in parallel with one another and in series with the warning light. So any individual thermal switch that is triggered will send a warning to the cockpit. Here you can see the thermal switch wiring circuit. There's our bus bar, our circuit breaker, we have our warning light, and then we have our thermal switches in parallel. You can see any of those thermal switches contacts close, I'm going to get my warning light. We also have our test switch there. That test switch is going to give current a path to ground and we're going to get illumination of our warning light. We can test for a bad bulb, make sure we have power. Here on slide 25, you can see thermal switches wired in parallel. Hopefully you can see the problem here. In order to get a cockpit warning, I'm going to have to heat up all three of those switches. Well, if they're located in completely different places, the entire aircraft's basically going to have to be on fire at that point. This is not a functional system. It is not practical. So we need thermal switches wired in parallel to one another. Slide 27, we have that same thermal switch wiring circuit, but now we have a break between the second and third thermal switches. If I heat up that third thermal switch, will I get a warning to the cockpit? No, I will not. What about the first two thermal switches? Yes, I still am connected to a power source, so if those close and I get a path to ground, I will get my cockpit indication. Here we can see a single loop thermal switch wiring circuit. Do you see why it's called a single loop? We have a single loop of wire there. Can I get power through the down leg to my thermal switches? Yes. Can I get power through the top leg to my thermal switches? Yes, I can. You can see at the bottom leg that also includes my test switch. But now I have two sources of power. That's going to allow me to have an open and still be able to get an indication if I have a thermal switch contacts closed. There's that same break as in the previous slides. Now, will any of the thermal switches work? Yes, they will. The typical single loop thermal switch circuit is designed to accept an open between any of the thermal switches, but a short to ground will cause a false indication. Make sure you understand this. If you go back to the circuit, you can see if I have an open, since I have that loop, I still have a path for current to get to my switch. My switch closes contacts to ground and I will get an indication. However, if I get a short, that is going to cause a false indication because now I have a path to ground for our current. Next up is the Fenwal spot detectors. They are like dual terminal thermal switches. If you look at the first thermal switches we looked at, they only had one wire or one lead coming out of them because they were grounded through the case. That is not the case with a Fenwal spot detector. Fenwal spot detectors are wired in parallel to each other between two complete parallel loops of wiring. The double loop arrangement allows the detection circuit to withstand one fault that is either a short to ground or an open without causing a false warning. So now we can handle an open and we can handle a short, one or the other, without getting a false warning. Slide 38, you can see this two parallel loop setup for the thermal switches. There's no set limit to the number of thermal switches in a system. We could have a system with one thermal switch and an indicator light, and we have a very simple fire detection circuit. Now the continuous loop detector. This one is significantly different than the thermal switches and the Fenwal spot detectors we've already looked at. A continuous loop detector or sensing system permits more complete coverage of a fire hazard area than any of the spot type temperature detectors. Two widely types of the continuous loop are the Kitty and the Fenwal. These continuous loop fire detector systems are overheat sensors, so they're not concerned with the rate of temperature rise. They consist of the Fenwal consists of a sealed Inconel tube, 0.089 thousandths of an inch in diameter, with a pure nickel wire central conductor. So basically we have a metal tube with a nickel wire running through the center of this tube. So this is a long sensing element that can detect an overheat condition anywhere along its length. In the Fenwal continuous loop system, the space between the tubing walls and the central conductor is a porous aluminum oxide ceramic insulating material that is saturated with a eutectic salt. So basically what this means is that that salt has a low melting point, relatively low. You can get a good idea of a cross section on slide 44. There's our pure nickel wire. There's our Inconel tube. We have our porous material with our eutectic salt. So what's going to happen when we heat this Fenwal continuous loop fire detector tube up, the eutectic salt melts. When it melts, that lowers its resistance to current flow and allows current to pass from the central conductor to the tubing. Now we have continuity, and we're going to get that alarm in our cockpit. On slide 45, you can see that little electrical arc going from that center conductor to the outside of the tube. This is how it detects. Some of the older Fenwal systems use ceramic beads wetted with eutectic salt. Same idea, just a little bit different construction. Now, the Kitty continuous fire loop is a little different It has two central conductors. The easy way to remember this is Kitty has two Ds. The Kitty continuous loop system has two central conductors, where the Fenwal only has one central conductor. One of the conductors is grounded to the outer shell at the end. The other conductor is positive. High temperature causes the thermistor's resistance to lower, and what are we going to get? The change in resistance of the detector elements are sensed by the electronic control panel circuit, which provides the alarm. So again, we're getting an increase in conductivity by that material that's separating those central conductors, and we're getting an electrical signal between those conductors. Our next type of system is the continuous element. Now, there's the continuous loop, which we talked about, the Fenwal and the Kitty, and now we have the continuous element. Again, they are a sealed tube. They can detect an overheat condition anywhere along the length of the tube, so they have that in common with the continuous loop system. But these systems use our good friends, the gas laws, for their operation. They operate distinctly different than our continuous loop systems. These continuous element systems are the Lindbergh, Systron, Donner, and Meggitt systems. Again, they operate on the general gas laws. The temperature of a confined gas increases. What happens to its pressure, given that its volume does not change? Well, its pressure is going to go up. So we have this sealed tube, and it is filled with gas. If you look at slide 54, give me one second. Slide 54, when that gas is heated up inside that continuous element tube, it pushes a little plunger, which closes contacts, and now we get our fire warning light. Lindbergh and Systron Donner systems use a gas-absorbing material. When heated, the material releases the gas, and the resulting pressure buildup activates a switch. So we're heating up this gas, which increases its pressure, which will close the contacts on the fire detection switch. The Lindbergh system is a little different in that it uses low voltage AC current for testing purposes. So in a Lindbergh system, when I go to test that circuit, I'm actually sending an AC current through the body of that tube. What's that going to do? Well, it's going to heat the tube up, which is going to heat the gas up, which is going to close those contacts. This is how we test the system. We actually heat the tube up just as if it was in a fire. The Systron Donner system has an overheat averaging ability, using helium gas as the element. Fire detection is by hydrogen gas that's released when the central titanium core is heated. So again, we're heating it and we have gas expanding. The Systron Donner is also interesting in that it uses a pressure-sensitive integrity switch that is opened when the helium pressure falls below a set value. This is the system that our T-39 Saberliner has. So if you look at slide 59, we see this Systron Donner system. At the top, we see a lead coming from the bus to one side of contacts. This is our normally open pneumatic warning switch. This is our switch that actually gives us the warning. Below it, you see our integrity circuit, and you can see it is normally closed. So that integrity circuit, that's our test circuit. It tells us, hey, our tube's okay. If we have a metal tube filled with gas, and we rely on the expansion of this gas in order to trigger our warning, what is going to happen if we get a hole in our metal tube? Well, the gas is going to leak out. Now our volume isn't held constant, so when we heat the gas up, it's just going to escape the tube. That is not going to allow us to get a warning if we do have a fire. So that integrity switch is designed so that if we get a hole in our tube, the gas escapes. That integrity switch is going to open. Now when we go to test the system, we're going to see that we have a fault and we'll have to look into it more in detail. Typically, you're going to have to replace the sensor element at this point, since that metal tube has been damaged. The Megget system came from a merger of the Lindbergh and the Systron-Donner. It's very similar to the Systron-Donner. The only real difference is in the testing circuit. The Megget test circuit uses an integrity switch that's normally closed, but is held open by the pressure of the helium gas. If the system loses pressure, the switch closes and illuminates a fault indication that means the system is no longer functional. So you can see it's similar to the Systron-Donner system, but instead of having a normally closed switch for its integrity circuit, this has a normally open switch for its integrity circuit. So that is it for the continuous element. Remember, the continuous element systems use gas. The continuous loop systems use a central conductor, or in the case of the Kitty, 2 central conductors inside a sealed Inconel tube. Next up is our rate of temperature rise systems. These are different from the overheat detectors in that they're not looking for temperatures above a given point. We're looking at the rate at which our temperature rises. We have the ever-present thermocouple system. Uses one or more thermocouple detectors wired in series to each other and a sensitive relay. The thermocouple detectors are made of 2 dissimilar metals, such as chromel and constantan, twisted together. Constantan, excuse me. If you look at slide 66, you will see we have 2 junctions. We have a hot junction, which is exposed to the air in the environment, and we have a reference junction that is inside the case of the thermocouple. What this thermocouple is detecting is basically the hot junction heating up much faster than our reference junction. The reference junction is going to take a little while to heat up when exposed to flame because it's inside that case. The hot junction will heat up much faster. When the dissimilar metal junction is heated, it produces a voltage. The voltage will send a small amount of current through a closed circuit. Sensitive relay closes the slave relay, which illuminates the warning light. You can see the sensitive relay controls the slave relay, which actually controls current to the warning light. When the test switch is activated in a thermocouple system, it sends bus current to a heating element in a sealed tube. The heater heats up a thermocouple, also in the tube, which then sends the current through the detector circuit and the sensitive relay. So we are heating up the thermocouple just as if it were exposed to a flame. In the rate of temperature rise system, the reference junction is inside the case of the thermocouple. When the exposed twisted junction, or the hot junction, heats up faster than the enclosed section, the reference junction, that's where we get our voltage produced by these 2 dissimilar metals. If the rate of temperature rise of both sections are the same, then the 2 voltages cancel each other out. So if you have these in an engine area and the reference and the hot junction warm up at the same rate, we're not going to get a warning, regardless of how hot it gets. That's the whole purpose of the rate of temperature rise. Now, if you have a fire in there, that hot junction is going to heat up much quicker. We're going to get our warning. This is not an overtemp system. It is a rate of temperature rise system. If the hot junction and the reference junctions are heated at the same rate, at the same speed, they will not produce a voltage. And we'll look at this on our mock-up when we get into practical time. If an engine heats up very slowly, the active and reference thermocouple junctions will heat up the same rate. We're going to get no current, which is not going to close the sensitive relay, which is not going to close the slave relay, which will not give us an alarm. The thing about the thermocouple system we have to pay close attention to polarity. The thermocouple fire detection system requires a polarity test if maintenance has been performed on the thermocouple detectors. If we put one in backwards, we could cause real problems. The test makes sure that all of the thermocouples are hooked into the system in series with each other, and that if a fire enveloped two thermocouples, the current from one does not cancel out that of the other. Let's think about this. We have two thermocouples. We have them connected in opposite polarity, and they both heat up. One's going to set out a positive voltage. One's going to set out a negative voltage because it's hooked up backwards. Those two voltages are going to cancel one another out, and we're not going to get a signal. That is the most important test for the thermocouple system, and you're going to conduct that test for me on the mock-up. And then we get to the photoelectric sensors, or the flame detectors. They detect the amount of infrared light in an enclosed area. Here in slide 80, you can see one from the King Air, available for the low price of $1,675. Flame detectors are placed so they can detect infrared radiation in a given area. So infrared radiation given off by a flame. Infrared radiation from a fire will activate a relay circuit and an amplifier, which sends electrical power to the cockpit fire warning system. The flame detector system has a detector unit, an amplifier to amplify a signal and send it to the cockpit warning alarm. Here's slide 82. Here's our flame detector. It senses the infrared rays from that flame, and it sends a warning to the cockpit. Smoke detection systems. Obviously, they're not going to be used in engine nacelles. Can you see the issue? Most engines are going to produce some smoke. Usually they're going to be located in cargo and baggage area, lavatories, and they have a couple different methods of detection. Why smoke detectors in a cargo bay? Well, flame detectors are good, but you could see if I have an irregularly shaped cargo area, or it's full of boxes, and I get a flame on one side, but I have a bunch of boxes stacked between the flame and my flame detector. Is the flame detector going to work? And chances are it's not going to work. Now, if I have a fire in the cargo compartment and I have a smoke detector, that smoke is going to fill the area, and I'm going to get a warning through my smoke detector. Cargo compartments may be very hot and humid air with humid air in them, and then when the air I apologize. Cargo compartments may have very hot and humid air in them. So then when we take off and we get to altitude, the temperature is beyond the ambient air's dew point, right? We're going to have moist air in there. So we have a bunch of different smoke detector units. They work on different methods in order to adapt to these. We have the visual smoke detector systems. These are the older systems. Indication is provided by drawing smoke through a line into an indicator. When smoke is present, a lamp within the indicator is illuminated automatically. So it basically sets off a light inside the smoke detector unit. Photoelectric smoke detectors, or optical detectors, measure light transmissibility in the air and or reflection or refraction and or absorption of certain wavelengths. Photoelectric are today's industry standard for smoke detectors. Light refraction, and light reflection smoke detectors sense light that is reflected from smoke particles passing through a chamber. Slide 89, you can see a little diagram of the photoelectric type smoke detector. We have on the upper left our long life LED light source, upper right our photosensitive diode, lower left we have our test LED, lower right we have our light trap. So you can see here we have that LED light shining into our light trap. Everything's fine. We are not having a warning. There is no smoke. We just have air. Now in slide 90, you can see there is our smoke passing through our detector. And what's going to happen when the smoke particles pass through? They're going to reflect light from that LED light source back onto that photosensitive diode. When that light hits the photosensitive diode, it is going to trigger the warning in our cockpit. Slide 91, you can see how the test LED works. It just lights up a test LED, which shines light to the photosensitive diode and will cause it to produce a signal. That's how we know that the system is working. The other gas we have to worry about in aircraft is carbon monoxide. We've talked about this before. Carbon monoxide is a byproduct of combustion. When we use combustion heaters and heat exchangers to heat the cabin, obviously if we have an exhaust leak, it can cause us major problems with carbon monoxide in the cockpit. So we have carbon monoxide detectors that are used to sense the presence of carbon monoxide gas. We're going to locate these in cabins or cockpits. Typically, they will change color. They're just a little color disc that's going to change color in the presence of carbon monoxide. The yellow silica gel with silicomalabate and it's catalyzed by palladium sulfate. So if it's a yellow disc, it's going to turn green in the presence of carbon monoxide. We also have the tan variety. When the tan variety is exposed to carbon monoxide, it is going to turn black. How do we return these to service? Well, we throw them away and we get a new one. Simple as that. I like slide 96. It shows the effects of carbon monoxide in parts per million. So in 35 parts per million, we're talking headaches and dizziness within 6 to 8 hours of exposure. As we go from 100, 200, 400, 800, 1600 parts per million. At 1600 parts per million carbon monoxide, we're going to get headache, dizziness, and nausea within 20 minutes. Death in less than 2 hours. Notice 12,800 parts per million, or 1.28% carbon monoxide. Unconsciousness after 2 to 3 breaths, and death in less than 3 minutes. It does not take much carbon monoxide to have very detrimental effects on the human body. You can see that is 1.28% of the atmosphere that you are breathing. So it's very important that we keep an eye on carbon monoxide in our passenger compartments. 97, 98, here are just some photo examples of these carbon monoxide detectors. You can see tan turns to black, yellow turns to green in the presence of carbon monoxide, not to be confused with carbon dioxide. Slide 99, we have the Guardian Model 353P-101. It can detect carbon monoxide as low as 10 parts per million and up to 999 parts per million. Back in 2008, it was about $460. So you can see the technology to detect carbon monoxide is progressing. The thing is that these disposable, cheap carbon monoxide detectors work. They're cheap. So a lot of times for aircraft owners, there's not a lot of motivation to switch over to these more expensive units when I can just swap out a unit that costs a few bucks. Anyway, this has been the first fire detection PowerPoint. I hope this helps you out. Let me know in the comments if the videos are helping you out, because they take a little bit of time to produce. I'm trying to make them a little more slick and increase my production value for you guys. Let me know what you think. Make sure you take the quiz. Again, fire detection systems will end on 5/21 when we will go into fabric covering. All of you stay safe out there. Thanks for tuning in with me. Hang in there. Be safe. Bye-bye.